This is the first of a few videos that I'm making for review before we start Calculus 2. I'm really trying to focus here on some of the things that you would have covered in Calculus 1, but may not have as fresh on your mind. And these are all things that will have a big impact on your success in Calc 2. So the first one is going to be talking about derivatives in general, but we're going to start with the chain rule because the first integration technique that we're going to talk about a lot is integration using substitution. And that is, in a sense, well, it's exactly just using the chain rule backwards. So we'll start by reviewing the chain rule. Here's an example of a formula of a problem where we're asking for the derivative. And in this case, we actually have a couple of choices for how to do it because we can, oops, wrote on my page. We have the option here because f of 5x plus 3 squared that we have here to take the derivative of, the algebra there is not too bad that we could have just expand that. If we just expand, and by expand here I mean think about FOIL, that's 5x plus 3 times 5x plus 3. And when you do that, you'll get 25x squared plus 30x plus 9. If the 30x surprises you, go back and actually write 5x plus 3 times 5x plus 3 and try to multiply it out properly. Dropping the 30x is an indication of an algebra mistake that will mess you up in other problems. But this is what you should get if you expand the 5x plus 3 squared properly. And then we can just use the regular power rules. The derivative of 25x squared is 50x. The derivative of this plus 30x is plus 30. And the derivative of this plus 9 constant is just 0. So we should get the derivative formula is 50x plus 30. On the other hand, we can think about this function, 5x plus 3 squared, as being the result of a substitution. Specifically, we could think about the formula g of u equals u squared, where someone just then replaces the u with 5x plus 3. So if you think about this as your function, g of u is u squared, and then you replace the u with something more complicated, 5x plus 3, then that's how you would end up with this kind of f of x formula. So the goal of the chain rule is to say what the derivative formula for this composition of functions will be based on knowing the derivative rules for these two component parts. Specifically, if I know the derivative rule for this g of u, and I know the derivative formula for this u, then I should be able to chain those together to get a derivative formula for this guy that's composed, that's the result of composing those two. If we want to see why the chain rule works, the easiest way to do that is to think about how one would estimate a derivative of f at a particular point. And I know this is a sea of numbers here, but let me just point to the salient parts. If I'm trying to estimate a derivative f prime of 2, I can do that by just finding the slope. This is rise over run slope between 2 points close together, one of which is the input 2. So here I have the input 2, its corresponding y coordinate, the input 2.001, which I've picked because it's close to 2, and the corresponding y coordinate for that. And so if I think about what that's going to look like without doing the arithmetic, it'll look like this if I try to plug those numbers in. Simplifying inside the parentheses tells me this is 13.05 and this is 13. And now the next step is kind of weird, and this is me just knowing where I'm trying to get to. These two things are equal only because this is a fraction, this denominator here matches the numerator here, and so these would cancel, and I would end up with this over this, which is what I have up here. So it seems like a weird step, but I'm writing this fraction as the product of two fractions, and it's legit because the denominator of the first one matches the numerator of the second one. The reason for doing that is that I didn't recognize this guy as the slope between 2 points on the squaring function, where one of them is 13, the input 13, and the other one is near the input of 13. So this quotient would be an approximation of the slope of the squaring function at the input 13. Similarly, this guy, it may not look like it at first, but this 13.005 and 13, those actually came from plugging in 2.001 and 2 into the u function. So this quotient is estimating, and you can see it better here, this quotient is estimating the slope of the u function at 2 points close together, one of which is the input 2. So the long and short of it is that this product is the approximation is an approximation of the slope of the squaring function at 13 times the approximation of the square of the u function at 2. And since 13 is u of 2, we can write it this way. So that is exactly why the chain rule works the way it does. If we want to write it in a simpler look at fashion, it would look like this. Here's the chain rule. So it's the derivative of the g function times the derivative of the u function. The only caveat for that is that the g function that's going to be the function in terms of u. And so when we do this derivative, we're talking about the derivative with respect to u. So g of u is u squared, which means g prime of u is 2u. So this guy is 2u. The derivative of u prime of x is just 5. Right here's u. So the derivative of this function is just 5. So this is what I would get applying that idea of the chain rule, but I'd like my answer to be in terms of x. My problem is in terms of x, so I don't really want my answer to be in terms of u. So I use the fact that I know that u here is equal to 5x plus 3. So the chain rule straight up just says this guy is 2u times 5, but if I want to write that in terms of x, that means it's 2 times this guy times 5. And that ends up being 50x plus 30 if you multiply it out. And if you remember, that's what we got when we did it the other way. So the statement of the chain rule when we use the difference notation, and when you think of it this way, it makes why it's true a little bit more obvious. If we just use the letter y for g of u, then what we're trying to find here is the derivative of y with respect to x. And so these two steps, this g prime of u times u prime of x, is really saying dy du times du dx. And you can see how it looks like there's something that should be canceling there, and that's really what we were just talking about in terms of the difference quotients. So this is what the chain rule is saying, that if you want to do dy dx, you can do that as dy du times du dx. In more functional notation, this is what we had on the previous slide. And so let's just see how we can answer a derivative question by matching things directly to that formula. So here's an example. Let's find the derivative of the square root of x squared plus 1. So in this case, the g of u function is square root of u. That's our outside function. And the inside function is that u equals x squared plus 1. So in other words, I'm taking the square root function and I'm changing the input of it into this more complicated x squared plus 1. That's what I mean by these functions look like they come from a substitution. So the chain rule says f prime of x is g prime of u times u prime of x. So g prime of u, that's a problem here. That means I take this thing and I find the derivative of this with respect to u. Now, if you don't recall, the way we would do that is the square root of u is really just u to the 1/2 power. And so what's happening here is just the power rule. The derivative of u to the 1/2 is 1/2 times u to the minus 1/2. So that's what's happening here. And then that's multiplied by u prime of x. And of course, here, this is u as a function of x. The derivative of x squared plus 1 is just 2x. So just like before, this is technically the answer, except it has both u's and x's in it. And our original question was only in terms of x. And so it's only polite to have the final answer be in terms of x. So all I have to do to get the final answer is change the u into what it's equal to in terms of x. So that'll always be written down. So that's the process that I can use. For a derivative problem, I can formally figure out what is my g of u and u of x. And then I know that my derivative is just g prime of u times u prime of x. And that works in general. Now, in practice, it may seem like when you took Calculus 1 that there were just an infinite number of things to take the derivatives of, but really there aren't. There's only a handful of functions that we have learned derivative rules for. You learn derivatives for things raised to a power. You've learned derivatives for trig functions, for exponential functions and logarithmic functions, and maybe for inverse trig functions. But it's certainly not an infinite number of things that we have ever had to deal with. So it actually, in practice, if we're working with functions that are built out of those elementary functions, there's only a handful of things that the outside and inside functions can look like. And so instead of memorizing one general chain rule, some people find it easier to just remember sort of the chain rule versions of each of the derivative rules that they already know. So here's what I mean by that. So if I'm thinking about the power rule, in other words, if my outside function is g of u is just u to a power, p, then this is what the chain rule says. It says the derivative of g of u should be the derivative rule for the power, which is just this. The power comes down front, and the power gets reduced by 1, and then times the derivative of the inside. You notice I'm writing these little boxes because I want to emphasize that whatever is inside the parentheses here is exactly the same thing in here and exactly the same thing here. And you'll notice when I do these derivative problems, I will always write down this whole first step. I rarely do this in my head. And the reason is I want to make sure that I have written the rule down correctly before I then do the rule. So I'm a fan of writing down the rule you're doing and then doing the rule as two separate steps. And if you follow that lead, you'll very rarely make the common errors. So for example, if we apply that idea to this problem, the one we just did, then as I said before, that is something raised to the 1/2 power. So notice that what I've written here, and I've put a box around it inside stuff just so that it looks exactly like this. So here was what I said I was going to write down as my rule, and here is what it looks like when I write it down. I needed to make a bigger box to contain the x squared plus 1, but notice that what's in the box is the same in all three places. So that's what the chain rule for power functions says. Then to actually do it, the only step that I haven't resolved yet in this sentence is this guy over here, this x squared plus 1 prime, but that's just the derivative of x squared plus 1. That's just 2x. So when I get to, I only need to do one more step. I get to here, and that's perfectly fine as a final answer. Just so you can review some algebra as well, I have gone ahead and simplified that by multiplying this 1/2 times this 2, and then rewriting this negative exponent as an expression in the denominator. So this is what it does end up simplifying to, but this is the right answer, even to this point. And notice that all I had to do is, first of all, write down the formula, and then second of all, do that one derivative. So it doesn't require too many steps. And if you do that in 2 steps, you'll very rarely make a mistake. Now, the power rule was just one of the rules that we learned. Here's some examples. I'm not going to go through all of these examples. If you're in my calculus class, you have gotten a worksheet that went with this video. And on the worksheet, there's these same problems are there with space to actually work on them. I will put a slide up at the end that has the answers to these. So if you want to work on these, pause the video and work on these 3 problems, and I'll come to the answers later. But what I was saying is the power rule was only one of the derivative rules that we learned about. Here are the rest of them that you would have learned about in Calc 1. And each of these is just the derivative rule you learned about, but it's the chain rule version of that formula. So when we have the derivative of the sine of something, the chain rule tells us that's the cosine of that same thing times the derivative of that thing. That's what this first one is saying. And each of the rest of them are along the same lines. So this is the minimum set of derivative rules that you should know as we start Calculus 2. The ones that you may not have done in much detail before are these ones down here for the inverse trig functions, and so we'll spend a little bit more time on those. But in terms of actually following derivative rules, they're just 2 more things to add to your list of rules to look for and to use in the context of problems that are assigned. And so in using these rules, you'll see we can answer other derivative questions. I will do one of these just to make sure it's clear. So this first one, for example, asks about the derivative of the cosine of something. And so again, my practice would be, let me just use black. My practice would be to write down what the rule says. So if you look at the previous slide, you'll see this is what the derivative rule for cosine looks like. On the slide, there will be a box. It'll say derivative of cosine of box is minus sine of box times. So again, the box shows up in all three places. It's identical in each place. And then to finish the problem, all I need to do is resolve that one derivative, which is not hard. The derivative of 3x squared minus 7 is 6x. So this will be my answer to problem number 4. The other 4 of these, plus the 3 that on the previous slide, are answered here, so that you can refer to them if you have time to give them a try. And you'll also find links on my review page to the Khan Academy site, which has not only videos on very particular versions of these, but also has little quizzes and self-assessments that you can do to get yourself feedback on whether you're doing them correctly.